All right. Okay, so we're going to start this problem here, looking at kinetics of rigid bodies. Let me just make sure I don't miss any names of points or other things. So this is a very simple problem. It may still take me 1 or 2 lectures or 1.5 lectures, but this is a simple one. We're going to start simple. It's really for educational purposes because there is only one rotation here. It's really not that big of a deal, but you will see it still takes quite some time if you want to think through it and try to avoid making mistakes. So inclined plane, which is the ground, and it's also an inertial reference frame. And then we have this cylinder, basically, which is a rigid body. Point of contact is Q. The center is C. The radius is R. And we say that we represent its rotation with an angle theta between the direction which is normal to the plane and a point that you pick on the cylinder, at the edge of the cylinder. The mass of this is m. There is roll with no slip, without slip. And what else do we need to know? There is gravity. I don't know what's going on. They're destroying the building. Okay, so good. That's all we have. And so I want the differential equations of motion. Let me, I don't need to write that. So as usual, that is supposed to be the center, by the way. I don't know if it really looks like the center. What we need to do is I want to hear you guys thinking with me through this thing, because it's really, we are at a point where you need to be able to attack these problems completely by yourself. This is a rigid body, which means you start without even writing anything. You start looking at the problem and you say, okay, that's a rigid body. In general, has 6 degrees of freedom, but it's going down the incline. And so in general, it will be something that needs 6 equations of motion, 6 differential equations of motion, 2 for the translation of a point, center of mass, for example, and 3 that represent somehow orientation. So 3 differential equations, for example, with 3 Euler angles. But I'm telling you that this is rolling down the incline, and the fact that I'm giving you an angle should be also a clue for you, right? This is probably going down to just 1 differential equation. The center of mass, it's moving on a straight line here, parallel to the incline. So if you can find the differential equation in theta, you're done. This really requires 1 differential equation. And again, if I give you a problem and I give you the angle, that's a good indication that you probably just need to focus on that variable. So we want to write these differential equations of motion in terms of the differential equation of motion in this case, in terms of the parameter that represents the state of this rigid body, which is only 1 in this case. And so that's nice thinking that you need to go through at the beginning. 1 degree of freedom, 1 differential equation. I'm not going to look for more than that. Now, as in every problem, what we do first is kinematics, right? You solve for kinematics, then you look at the forces and moments in this case. I'm rewriting the same thing, I'm sorry, kinetics. And then you combine them together. In this case, that means Euler's laws, right? Okay? That is really the sequence. Now, what are the things do you need to calculate to solve for kinematics? You guys tell me. So we're going to start from kinematics, of course.
Reference frames, coordinate systems.
Right. Those are, well, we'll build them. But the end goal of this, where am I going with acceleration of what? This is not a point anymore.
Of the rigid body.
The rigid body doesn't have an acceleration. Points have accelerations, linear accelerations.
The center mass.
Center of mass, right? Think about Euler's laws. We're going to use these two, F equal ma of center of mass in an inertial reference frame, which I called G in this case. And this is the summation of all external forces, all forces acting on the rigid body. And then we've written these in several different ways. This is d dt h bar n is equal to m bar. This is one way, right? or we also said d dt. Well, this is actually a derivation. The actual law is d dt in g of h o, where o is an inertially fixed point, is equal to mo, but we derived from this that this is valid too. And then there was another one that I gave you, and I probably need more space. With respect to a generic point, this is still the second law. It's just written with respect to different points. This is center of mass. This is an inertially fixed point. And then with respect to a generic point, you have d dt with respect to the ground, which again, it's an inertial one, h q in g. Okay, you guys tell me, what is this equal to? mq, and then what else do I have here? Go back to your notes. We derived this, I think, last time, right? Is this right? Does it look right? Check your notes. May make mistakes. I don't like to memorize formulas. I just like to remember there is a formula that has to do with angular momentum, and it's associated, and it's the second law of Euler. So okay, you told me that for kinematics, I definitely need the acceleration of center of mass with respect to g in this case, which is inertial, if I want to use the first law, right? And some problems you may not need to use all of them. And these are just different flavors for the second law. So now we start thinking about what we need for the kinematics part of the problem to implement the second law of Euler. What do I need? Something that has to do with kinematics. I'm not looking at the causes of motion. I'm not looking at force and moments for now. I'm looking at this other side. So I probably need h. And h has in it the angular velocity, which is part of kinematics, but it also has the mass properties because there is an inertia tensor. So what I'm telling you, you guys want to do in every single problem, you look at computing h bar. Why? I'm sorry, I'm mixing n and g here. N is inertia. So why am I telling you that? Well, this is pretty obvious. Acceleration of center of mass, you want it if you need to use the first law. Why, since I'm giving you these three versions here of the second law, why am I telling you you go just straight to computing this first? Why do you think that's the case? Without even thinking. If you're doing the kinematics part, you do acceleration of center of mass, and then angular momentum with respect to center of mass. Why? There is a reason why. We calculated it last time. We demonstrated it. What is this? Tell me, what is this in general? How do you write it? Did it go too fast last time?
You mean the rotation times the tensor?
Rotation times tensor. Say that right. You're almost there.
The tensor acting on the rotation matrix.
It's the tensor of inertia. That's the name. With respect to the center of mass of the body, let's start giving names here. G is the ground, and this is the disk D, right? So of the disk, dotted with the angular velocity of the disk with respect to the ground. But again, okay, this is what it looks like. But why am I doing it with respect to the center of mass? There is a specific reason why I'm doing it with respect to the center of mass. We at some point said parallel axis. If you remember, parallel axis theorem is really something you don't need. You can always move to another point. So you can always bring your calculations back to the center of mass. Why? What happens to this guy here when I do it with respect to the center of mass in a body fixed coordinate system? We did it. Okay, guys, this is something that you really need to understand. This is basic stuff you need to capture in your mind once and for all. What is that? If I start writing that, how does it look like? It's a tensor. How do you write it? Can you get me started here?
It's a matrix I1.
It's not a matrix. It's a tensor. I want to write it as a tensor. Looks familiar? This is one of them. And then I keep going. I'm not going to write the whole thing here. It doesn't make any sense to do it. You just keep going here with all these tensor products and so on and so on and so forth. Okay. What happens to these things? What are they? Those are constants, right? Numbers? Where do I get those from? A book. So, actually in the book, as we'll see in this problem, you don't even get the products of inertia because you use special body fixed coordinate systems where they go to 0. So you only have the I11, 22, and 33. But these are in tables. These are lookups. These are lookups. Okay? So that's why when you start a problem with rigid bodies, you find the acceleration of center of mass, you find the angular momentum with respect to the center of mass because you know you can write it like this. And once you've done it with respect to the center of mass, then you can move to other points because we have a specific expression to go to another point if we need to. Let me write that just in case. What is that expression? So I don't need this, right? Are we convinced of this? Right? You know how to write the h angular momentum with respect to the center of mass for given shapes. Of course, this is one of them. For a cylinder, you have it in the book. Not all shapes are available, but usually for problems, you have them in the book. So, okay, yeah. So if I need to move to another point to solve my problem, then I know this, right? VQ in G in this case minus V bar in G. Remember this? So first you write this and you know how to express it. Then if for some reason you need to move to another point, well, you just need to compute this cross product. You need to know that point where it is, of course, and its velocity, and you know that information for the center of mass definitely because you've gone through the pain of computing its acceleration. So I know that at this point it looks like you have so many different things you can do, but it's not true because I'm going to break it. I'm going to reduce the things you need to really remember to just a couple. The first law, that's pretty easy, right? And this is the only one you really need to remember in terms of the second law. Why? Because this is valid for any point. If this point Q happens to be the center of mass, guess what? This goes away and you get this version. If it becomes a body, an inertially fixed point, guess what? Its acceleration goes to 0. It comes down to this. So you don't need to remember different flavors of the same formula. You just need to remember one. And since you can do all your problems with open book, you don't even need to remember. You just need to know that there is one that is generic for any point. So second law of Euler can be written like this for any point Q. So if it makes it easier for you to go to a point that is not the center of mass, well, you do this. You transport your h bar to another point, and then you apply the second law, like that. That's really, I know it sounds like a lot, but it's just a few things you need to do. Then the calculations may be elaborate, but that's a different story. Does it make sense? Is the flow making sense? This is the high-level thinking that you need to have pretty clear in your mind before you start doing anything. Okay? We're good, I hope. Well, let's start doing it then. Kinematics, so, well, I know, we remember that this is inertial. Acceleration of center of mass. Who wants to help me here? How do I compute the acceleration of the center? Oh, well, we're skipping the main part, right? The reference frames and coordinate systems. Let's do that. Let's do that. Okay, reference frames. See, nothing changes. This is all stuff that we've done at the beginning with a single particle, and it's still there. So we said G is the ground, right? And it's also inertial. And then the disk is another reference frame. And let me pick the coordinate system here. What do you want to do? Origin? I don't care. What are you going to do? That's the reference frame G. So I'm picking the coordinate system fixed in G. Again, all we've done from day one, it's going to be here every single time. You can't forget anything. It's all connected. What do you want to pick? Ground. Give me a point.
Q.
You want to do Q? No, you can do Q. I mean, I don't care. Q when? Want to do this? Okay. Is that okay? It's not going to change things. When you start computing vectors, instead of going from C to the other points, you would go from Q to the other points. It shouldn't really change things. But we need to know that this point is not going to move in G, so you have to freeze it at a certain time, and then it doesn't change in G. And then I want to say maybe EX down the incline. And since that disk is rotating this way, I am tempted to do z-axis that go into the page, because maybe my angular velocities and accelerations will have a plus instead of a minus. And then what is EY? EY is EZ cross with the x. And so I hope we remember there is rho without slip here. Let me remove this part. So this will be your just the coordinate system, right? EX going down like this, EZ, it's going inside, and then EY is which way? Like this? Make sense? Okay, that's done, and then let's do the second one, the disk. Origin probably at C at any time. It's a fixed point in the disk, its center. And then let's say little ex along CP, right? EZ equals little ez equals big Ez, and then EY is little ez cross with little ex. And so this is going to be the situation here. This would be your little ex. The two EZs are the same, right? Going in. And this is your little EY. And need to be careful here. This will be your angle theta, right? If we do it that way. Make sense? This is an open choice. Okay, now we can start computing this acceleration of the center of mass. How do you compute the acceleration of the center of mass? See, everything comes back. There's no escape. Remember what I told you is going on here? What does it mean that the disk is rolling on the incline?
It means that the relative velocity at Q is 0.
Is that the way we expressed it? Tell me something I can write here. Yeah, that's one way, but velocity, remember Q is the point of contact. That point is really different points that happen to share the same location in space in one instant. It's the point Q that belongs to the disk that the next instant in time will be somewhere else. And so there will be another point touching the ground, and the point Q that corresponds to the ground, which also will be not touching the disk at the next instant in time. And then there is this imaginary point that is representing the contact, which is describing a line on the ground. As I told you, I believe, a few times, you can imagine the disk leaving a trace with ink or something, so that would be the line that you see. By the way, what is this point doing here? This point that goes down the incline, what is its velocity? I don't want an answer, but can you relate it to something else? That point down here is doing whatever C is doing. They're going together, right? They're going down. Okay, but anyways. So the condition of roll without slip is that the velocity of the point Q as seen belonging to the ground, so the point Q that is part of the ground, in the ground reference frame, which is obviously 0, because it's the velocity of a point of the ground with respect to the ground, is also equal to the velocity of the point Q as part of the disk seen by the same frame, reference frame. So this tells me that the velocity of Q is 0. Vector. That's the roll condition. Good. What's next? I still have to find this acceleration. What do I do? There's a few things you need to remember from this class, but you need to remember them. Otherwise, you can't move on. So my goal is this point C. I probably want to have its velocity and then eventually its acceleration, right? That's how I would proceed. So can I make any use of this information to get its velocity first? Can I? You can imagine the answer is yes, but how? Tell me. That's a rigid body. When we started kinematics of rigid bodies, I believe the first thing we've done is computing a couple of relationships that are very useful, that only apply to points that maintain a constant mutual distance. In other words, belong to the same rigid body. Point Q and point C are 2 points on the rigid body. What is the relationship between those two for the velocity? Come on, don't be shy. Disk with respect to the ground cross right? Now this is 0, we said, right? Okay, so what is omega dg? Okay, it's just one rotation here. And one is RC minus RQ. It's the vector going from Q to C, right? What is that?
So RC minus R
minus RE big EY, right? With that coordinate system I picked, that's what I get. So this is, what is it? EZ crossed with EY is minus EX. So this is theta dot R big EX. Kind of makes sense if you think of this as, it's rolling down. So this point is probably going in that direction as it rolls. Cool. So what is the, and of course I'm focusing on C because I forgot to tell you. It should be pretty obvious that this is also V bar. It's a uniform disk or cylinder of mass m. I guess I should have specified that at the beginning. So that's the center of mass. Okay, so if that's the velocity, you need to tell me in 1 millisecond what the acceleration of the center of mass is.
R theta dot EX.
All right.
I have one question.
Yep.
Is the reason why RC minus RQ equal to negative capital R EY because RC is 0? This was measured from the origin.
Yes, you can see it that way. Yeah, right. Yeah, so there will be, from here will be this, you only have RQ with a minus in front, and so, yeah. Or the way I see it, it's up to you. It's a vector that goes from Q to C, right? And so if I project these vectors, I get the same thing, minus R. So yeah. Either way, as long as you have the right vector. Okay. I've done the first part of kinematics. So let me write it here. Okay, now, I told you can do whatever you want. You can pick a point for the second part. But first, we do the center of mass. For h, I'm looking at h now. I'm still doing kinematics here. H bar in G, I know it's I, the tensor of inertia bar of the body D, disk, times omega dg. All right, so this is, we're not going to cover all this geometry that is involved with different shapes of bodies, but I can tell you that a cylinder, and you can look this up in your book, so if this was actually in 3D, a cylinder, when you pick those body axes that we picked, little ex, what is this, little ey, and then this ez here, for example, this is, for this kind of body, is called the principal axis coordinate system. For each body, it doesn't matter how complicated, rigid body, it doesn't matter how complicated the shape is, there is always a body fixed coordinate system with the origin at the center of mass and the axis oriented in such a way that this tensor of inertia only retains the I11, I22, I33 terms. There's no products of inertia, only the moments of inertia. I don't expect you to compute those axes. We'll see problems where the shapes are, in general, kind of obvious. So where there is an axis of symmetry, that's definitely one of the axes of the principal coordinate system. And in this case, it doesn't really matter how you orient Ey and Ex because the section is a circle and the mass is uniform. So we really are not going to focus on that. There's all sorts of problems you can solve by having weird shapes, and you compute the basically the inertia tensor with respect to just a random coordinate system, and then people could ask you, now you tell me what is the principal coordinate system. But I don't expect you to do that because that's just mass properties, and you can look it up. So in this case, it's a principal axis coordinate system. So this means that my inertia tensor is really going to be equal to what? Let's see, I bar, what did I call, x, y, z. So let's say this is ixx, ex, circle cross, ex, plus I, y, y, of course always bar, ey, circle cross, ey, plus I, z, z, bar, ez, circle cross, ez. Now, I made a note to myself about what those are because I refuse to remember these values here. So ix, x, and yy, as you can imagine, they are the same. These are constants, as I told you. These are, if you look them up, is m, the mass of the disk, cylinder in this case, r squared over 4. And instead, about the ez, the symmetry axis, this is m r squared over 2. Lookup tables. Now, the beauty of this is when I do the dot product with omega, so I get this tensor dotted with, what was omega? Theta dot, little ez or big ez is the same thing, right? So what is left, really? Do you remember the definition of tensor product? A circle cross B dotted with a third vector C is going to be equal to B dotted with C A. So this is something you will have to apply between these two guys here, Ex, circle cross Ex, and Ez. And of course you will see an Ex dotted with Ez, which is a 0. Same story for this. So the only thing that is left is this one, right? The only one that survives. I'm just applying everything that we've seen, nothing more. So what am I left with? Really is m r squared over 2 theta dot is z. Is that the right momentum? Yeah. Yeah. That's all. This is a simple problem. This is just one rotation. If we get to do it, since you guys want to see also real-life applications, at some point I'll try to bring a gyroscope here, which is a three-dimensional object that can go around with 3 other angles that you need to use, and you will see how funny it gets when you have 3 rotations. But Still, this is a good problem. So this is my h bar. I write it here. H bar in G is mr squared over 2 theta dot little z, or big z. They're the same thing. Questions, concerns? Is it flowing okay? Is it making sense? You may have forgotten some things, but now maybe you're refreshing them. I have to do the same. If I'm not sure about what roll without slip means, I go back and check it on the book. Because I'm not going to write something down that it's kind of sort of okay, and then I use it, and the rest of the problem it goes down the drain. So that's why you use a book and you have 24 hours. There's no reason for rushing here. That's not the point. So now I have these two. I've done the kinematics. Let's look at the kinetics. Let's do the first part of kinetics, which is a free body diagram, right? So this is the free body diagram. I want to look at the forces here. Okay, what do we have acting on that disk or cylinder? Depends on how you see it. Gravity, we apply at the center of mass, right? mg. Cool. And then there's something going on with the floor here, with the ground, right? And we said last time, yes, there is a reaction that goes like this towards the center, the normal one. But then if this is rolling without slip, there must be something that makes it roll. There must be some type of friction here, because otherwise there's no point. Why would this have zero relative velocity? It will just slide down, right? So something is going on here, and it's not a dynamic friction, because we said there is no relative velocity, right? So it's what we call static friction. And for static friction, you can only tell me that that's the line of action and nothing else. You cannot write an explicit formula. So these two are unknown. So this is static friction. This is that thing that when you do statics and you balance a structure, you have to compute after you figure out all the other forces. All right, so let's write F. F is mg plus n plus F sub F. Let's use, what do we use? Whatever you want to use here. G is, okay, so we need to project G in some coordinate system here. And I guess I'm going to use the big E's, since I have the acceleration already in that coordinate system. So if this is EY, and this is EX, G is pointing down like this. What are the angles involved here? Is this beta? Okay. So it looks like it's mg, and then I have, what do I have? Cosine of beta? EY plus sine of beta EX. Makes sense? Okay, plus, then these are kind of nice. I can just directly use big EY and big EX, right? N would be n, some unknown value that multiplies EY. And then the other one is some unknown value that multiplies EX. Again, don't put minuses unless you know anything. There's no need. Okay, so if let me regroup this thing here. Let's see what we have in common. I have mg, let's do the EX, sine of beta plus F sub F. This is on EX, right? And then I have mg cosine of beta EY plus n EY. And this is equal to m theta dot r EX, right? This is the first law of Newton. That's exactly what I've just written here. First law. Now, does it give me a differential equation? it doesn't. If I do the dot product of both sides with big Ex, just to remove this, I still get this unknown here. So not that great. I probably have to use the second law. In some cases, if you figure things out at the beginning, you may not need to use both. But in this case, if I thought I was going to solve it with this, well, I'm out of luck. I need to use the second one as well. But let's write what we have. We actually have found that m theta dot big R is equal to what? What I have there, mg sine of beta plus force of friction, the magnitude, right? Agree? Okay, that's another piece of information. And now we have to use h. I told you to compute the h bar, but that doesn't mean that you're not free to pick.
Shouldn't the A have theta double dot? Theta dot?
It did have a theta double dot, yeah. Yeah, thank you. I lost it along the way. Good check. Dimensions. Okay. Now you have h bar. That doesn't mean you have to pick the center of mass, but we're going to do it with respect to different points. Actually, if we have the patience, we'll probably do it with respect to 3 different points. Again, this is a simple problem. You can do it in multiple ways. Shall we do it with respect to the center of mass first? So I do have this, and the equation is d dt. The second law will tell me that d dt in g of that vector h bar in g is equal to m bar. That's it, right? Well, this first term, it's pretty simple, right? Should be. What is d dt of h bar g? Can you tell me? Why?
R doesn't depend on time, and M also doesn't depend on time. And EZ is basically capital EZ.
It's fixed with respect to the ground.
Yes.
So you can take the derivative just of the only thing that is really changing with respect to an observer fixed to the ground, which is the angle theta. So this is m r squared over 2 theta double dot. Big Z, yeah. Or little z, doesn't matter. That's the derivative. That looks nice. And then this is what? This is the summation in general, right? It will be summation over I of Ri, position of the points where the forces are applied, minus the position of the center of mass, cross with all these forces that act on the different points, plus any pure torque that I would have, which in this case I didn't give it to you, so you don't have pure torque. Okay, so let's start breaking this down. I erased the free body diagram, I'm sorry. Probably should redo it here. This is the center of mass, of course, right? This is the point with respect to which I'm computing all those moments for the forces. This is mg, and this we had here was the reaction, normal to the ground, and the force of friction. Okay. Can you help me breaking this down now? What's the moment due to the force of gravity with respect to the center of mass? 0. Done. Then, this point is what we call, this is C and this is Q, right? So for both forces, you're actually looking at the point of application Q. So this Ri will become, for the first one, Rq minus Rc cross with N. And then you have the same Rq minus Rc cross with F sub F. Let's substitute a few things here. We said Rq minus Rc is what? I think we want to see this multiple times. Minus R big EY, right? Cross with N EY. Kind of makes sense that N is going, the line of action of N actually goes through C. So this will go to 0 as well. And then I have, minus R EY cross with Eb sub F Ex, which is going to give me what? Minus R F of F EY crossed with the S is EX is what? This is actually a minus EZ, right? No? Did I make a mistake?
Minus RC should be plus REY. The difference between here.
This? Isn't this the same vector?
Yeah, but that also should be plus REY because you are going from C to Q, not from Q to C. Previous time you used from
Before I add, are you sure?
Q to C. Yeah.
RQ is that. Oh, you're right. Yeah. Okay. This is plus. This is plus, so this is minus. Thank you. Yes, we were going to C before. Now we're going to Q. Right. Because you're computing the yep. Good. Okay, so this is what I have, and this is equal to that ugliness there. Well, actually, it's not that ugly. So I combine these two together, and I get my second law projected in the coordinate system that I want, which is telling me that mr squared over 2 theta double dot, I can remove this EZ vector at this point, right, is equal to minus r eb sub f. Nice. Now I have two equations that I can play with. It's this one and this one. I can eliminate the force of friction. Once again, this is a planar, simple problem, but it's good to understand the steps that you will have to follow for rigid bodies. So I have, let's see what I have here. So eb sub f from here is what? Is m theta double dot r minus mg sine of beta, right? I plug it in there, I get m r squared, right? Theta double dot over 2 is equal to minus m theta double dot r squared. I'm multiplying everything times r plus mg r sine of beta. That looks like a differential equation. Everything is known. This is a known angle, radius, g, mass. Everything is known except the angle. And that's what I want. Let's see if I put it in a better way. This is going to be 3 over 2, right? 3 over 2 m theta double dot r squared is equal to mg r sine of beta. Well, you can simplify a few things here. If you want, you can write it this way. Theta double dot is equal to 2/3 g over r sine of beta. Assuming there's no mistakes here, that should be your differential equation of motion. All these calculations to get that small equation there, which, by the way, is telling you that the angular acceleration of that is constant. So it's the angular velocity is going up as this disk is going down the incline, and it's increasing at a linear rate, and that's the linear rate with which your angular velocity is increasing. That's not a big surprise, right? Now, I went through all this pain doing it with respect, yes?
I'm a little bit confused.
Is there an error?
F of t equals m theta dot
F of f, f sub f. So this, I just got it from here.
Yeah, that's fine. But if you look over here, you see that this is minus rf of f, that is mr squared over 2 theta.
Yeah, it's the same thing. I don't know if it looks like a t, but that's an f.
No, yeah, that's fine. I'm
Oh.
just saying, and here you have f of f,
Mm-hmm.
and then what you substituting for it is the expression of minus r times f of f, not just f of f itself.
That's why I multiply times r, right? Didn't I? I change the sign of these, change the sign of these, multiply times r, the whole thing. So that's what I should get. So this is the same. This equation here is yeah. No, it's fine. It's this equation down here where I plug in f sub f. Yeah.
Okay.
fine. I mean, if we, yeah, sometimes skip steps, and I usually make mistakes when I skip steps, and this was not one of those cases, but it was just good luck. Okay, so as you've seen, in this case, I had to solve for, I basically had to compute both laws of Euler to get the solution. There is another way to do it. There is multiple ways of doing it, of course. Can I erase? We get it started, and then we, of course, continue next time, because I want to do it with respect to two other points. Now, what is the thing that was causing me to have to solve for both, to implement both Euler's laws? Is that I have these unknown forces, reaction and force of friction. What about picking another point that gets rid of them? Which one? Point Q, right? If I compute H now with respect to point Q, when I'm going to do M with respect to Q, N and force of friction, the reaction and the force of friction, they go through Q, so they will have no moment. The gravity will have a moment, but that's something I know. So how about now we pick, of course we just started here, and I invite you to do it. We pick point Q before I do it on Monday. Now, which point Q? There's a lot of points Q here. You can do whatever you want. You have the general version of second law of Euler, which is telling you the d dt in G of H with respect to a generic point Q of the it's equal to M with respect to that point Q plus RQ minus R bar cross with M acceleration of that generic point Q in G. So you can really pick any point. In this case, they happen to have the same name, Q. But so Q could be a point on the ground. It could be a point on the disk. I'll tell you, let's pick point Q on the disk. Why? What happens if I say that at time 0, the contact is here, and I pick this point here, Q, which is fixed to the ground. It's an inertially fixed point, right? What happens if I pick that one? Think about your forces here. What happens if I pick this guy here? Normal will still have a moment. So I mean, I'm not really helping myself that much. I will probably still have to do both first and second law. While if I pick point Q that is on the disk, that is the point that will always see normal and force of friction going through that point. Okay. And now you have to do a few things here. You have to now move that H bar to HQ. That's the first thing you need to do. Then you compute its derivative. You have to compute the moment of the forces with respect to the new point, which is really coming down to only the moment of gravity with respect to Q. Well, position of Q, position of center of mass, we know them. You need to tell me what is the acceleration of point Q. In this case, it means Q part of the disk, because we picked that point. Where do you want to start? I would start from rolling here. How do you, just for fun, you have to do all those things anyways. What is this? I don't want an answer right away, but I want the procedure to compute that acceleration. How would you do it? We have seen it in examples. Actually, I think we've done the same exact thing probably. Remember, this is rolling. So what is true about the acceleration of a point and the acceleration of another point on the disk? You fill it in. There is a relationship, the same thing we've done before between velocities. There is a relationship between accelerations of two generic points on the rigid body. And guess what? I do know this. I hope you know what's on the other side. We'll do it next time. So you can get to AQ. And then it's 35, and we'll finish it on Monday. It's the angular acceleration cross RQ minus R bar plus omega cross with omega cross with RQ minus R bar. There's just a few things you need to remember, or at least you need to know that they exist. I don't expect you to necessarily remember the details of these. I expect you to be able to open the book and go to that page. I'm done.